Yeah. So let's start with the revision session. So here we are going to start with week 5. So I hope the topics which we have covered yesterday is clear to everyone. Now in week 5, we are going to look at rank of a matrix, right? So rank of a matrix, for an m by n matrix, what is the rank? Rank is nothing but the number of linearly independent rows or columns. Either you can look at the rows or columns, right? So you can either look at the column space, that is the space spanned by the columns of A, or you look at the space spanned by the rows of A. Okay, so the dimension of the column space is the column rank, and the dimension of the row space is the row rank. So both of this will be equal. So either you can look at row rank or column rank. Both are going to give you the rank of a matrix. Okay, so in general, what is the way to find the rank of a matrix? You find the row echelon form. Rank of A is nothing but the number of non-zero rows in the row echelon form. Okay, and always remember, rank cannot exceed the number of columns or rows. Okay, because of this condition, rank of A is less equal to minimum of m comma n, and similarly this property may be used for doing some problems, right? So for example, if you are having a 3 by 5 matrix, what is the maximum rank for A? Rank of A is
3.
less than or equal to,
3.
3.
right? Okay, so next is null space. Let A be an m by n matrix. The space set of all x in Rn such that Ax is equal to 0 is called the null space of the matrix A, right? So already we have seen the same set with another name. What is that? These are nothing but the
Homogeneous solution.
solutions of the homogeneous system Ax equal to 0, right? And we have seen that this system will always have a solution. So this system is always consistent. And what is the solution?
0 solution.
Zero solution is always there. So this space can never be empty. So this null space is always non-empty because it contains the zero vector in the null space. Okay. And the dimension of the null space of A is nothing but the nullity of the matrix A. Okay. Fine. Now here is an example. You have a matrix A and you are considering Ax is equal to 0. Now for this following options, so you are asked to find what are the dependent and independent variables. So yesterday itself we have seen how to find dependent and independent variables. So the first column and the third column are containing the dependent
Pivot
Variables.
pivot
pivot
terms. So x1 and x3 are the dependent variables
variables.
and x2 is the independent variable.
Independent.
Okay. So now for this matrix A, what is the null space and nullity of A? How do you find the null
0.
space? So for finding the null space, you need to consider Ax is equal to 0, right? So if you consider Ax is equal to 0, you consider 1, 0, 0, 0, 0, 0, 0, 0, 1 times x1, x2, x3 equal to 0. So this gives you x1 is equal to 0 and
x3 is equal to 0.
x3 is equal to 0. So what do you get as the null space of A? So null space of A is nothing but set of all 0, comma x2, comma 0 such that x2 is in R,
Yes.
right? So this is the null space of A. Now what is the dimension of this null space?
1.
1, right? So what is the basis for this?
0, 1,
0 x 0.
0, 1, 0, that's all, right? 0, 1, 0 is a basis, right? Now you can say that this is a basis, and so nullity of A is
1.
okay. So what is that you can see is that x2 is the variable which is the independent variable for this matrix, and that contributes to the null space. So in general, what you can see is that the number of dependent variable corresponds to the rank of the matrix, and the number of independent variable corresponds to the nullity of the matrix. Okay, so here you have two dependent variables. So two dependent variable means what is the rank?
Rank 2.
Rank
2.
So rank of A is 2. And here you
2.
have one independent variable, which means your nullity is
equal to 1.
1.
1.
okay. Fine. Now,
Ma'am, ma'am,
yeah.
ma'am, this condition holds only in case of reduced row echelon form. This
See,
rank
how do you
and
find dependent variables and independent variables? You look at the row echelon RREF form only for finding the
yeah,
dependent and independent variables. That is how we define it, right? So you look at
right.
RREF form. If the ith column has a leading entry, then you call that to be dependent variable, right?
Obviously, ma'am, then I have to. This is only for the reduced echelon form, no,
Yes,
ma'am.
yes.
Fine, fine.
Okay. So next is the rank nullity theorem. For an m by n matrix A, rank of A plus nullity of A is equal to n, right? So now here is a problem which uses rank nullity theorem. Find out the value of A for which the matrix has nullity 1. So if the matrix has nullity 1, okay, so what is rank nullity theorem saying? Rank of A and nullity is given to be 1. So let's
1.
call this to be A plus nullity is equal to n. What is your n here?
2.
N is
2.
2, right? So your rank of A is
1.
1. So if rank of A is less than n, here it is less than n, then what does it mean?
Determinant equals to 0.
Determinant is 0. So determinant of A equal to 0 means what is the determinant of this matrix?
A
A
minus
minus
6.
6, right? A minus 6 is 0. It means you have A is equal to 6. Okay? Do you understand what we did
Yes,
here?
ma'am.
Okay, we simply applied rank nullity theorem and found the determinant should be 0. So using that, we found A is equal to 6. All right? Okay. So the next question, let nullity
Ma'am,
of...
sorry
Yeah,
to interrupt you, ma'am. I
yeah,
just
yeah.
want to know, ma'am, this statement, ma'am, if the rank is less than n,
Hmm.
if and only when if determinant is equal to 0, ma'am. Can you
Yeah.
elaborate little bit, ma'am?
See, what happens when rank of A is equal to n? We already know that when rank of A is equal to n, we know that the determinant is non-zero. It means what all the columns and rows are linearly independent. So we have a non-zero determinant. So the other way around, equivalent statement for this is that, so if determinant is 0, what does that mean? Rank should be strictly less than n, right? So
Okay,
this is just an equivalent statement of this.
fine, ma'am, fine.
Okay, fine. Okay, let nullity of the matrix A, which is of order 3 by 4, be 2. Find the rank of the matrix A. So again, rank nullity theorem only. So rank of A plus nullity of A is given to be
4.
2. Nullity is given to be 2,
2,
right?
2, 2.
Yeah, and what is your n?
4.
N
N
is
is
4.
4. N is 4.
So your rank should be
2.
2.
2.
okay. Fine. Which of the following options are correct for a square matrix A of order n by n? If the determinant is non-zero, then the nullity of A must be 0. True or false?
True.
True,
True.
right? Because
True.
if the determinant is non-zero, you know that the rank of A is n. If the rank of A is n, according to rank nullity theorem, nullity should be 0.
0.
0.
0.
If the determinant is non-zero, nullity of A may be non-zero, definitely incorrect.
No.
No.
If the nullity of A is non-zero, then the determinant of A must be 0.
True.
True.
Right?
True.
Because if the nullity is non-zero, it means your rank is strictly less than n. So we have determinant to be 0. Right?
0.
And then if the nullity of A is non-zero, determinant may be non-zero is incorrect.
False.
So all the 4 options are clear, right?
Yes.
ma'am.
Yes, ma'am.
Okay. So next problem is that you are given a 3 by 4 matrix and we are asked to find which of the options are true. So rank of A must be less than or equal to 3.
True.
Correct or not? True, right?
Yes, ma'am.
Nullity of A must be greater than or equal to 1.
True.
Correct.
Why is that so?
Not.
Number of columns is equals to 4.
See, here you are having an m by n matrix where n is equal to 4, right? So you know that rank must be less than or equal to 3. So here, this side you have 4. Here the possible options for rank and nullity. So rank can be 3, 2, 1 or 0. So what can be the corresponding nullities? 1,
1, 2,
2,
3,
3,
4.
4.
4. So nullity must be greater than or equal to 1. Nullity cannot be 0. Okay.
Yes, ma'am.
So this option is correct. If A has two columns which are non-zero and not multiples of each other, while the remaining columns are linear combination of these two columns, then nullity of A is equal to 2. So totally how many columns you have?
4.
4.
So let us call the column vectors to be V1, V2, V3, V4. So out of this, it is given that only 2 are linearly independent.
Rank equals to 2.
So this says that rank is 2. So rank of A is 2 means the nullity should be
2.
2.
2.
right. Here it is given, the same statement is given with nullity 1. So this is incorrect.
Incorrect.
This is clear, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So next, what is a linear transformation? For a linear transformation T from V to W, where V and W are vector spaces. So for a function T from V to W, if it satisfies these two conditions, then we say that T is a linear transformation. Okay, so for any V1 and V2 and for any scalar C, if these two conditions are satisfied, then T is a linear transformation. And what is an important property of a linear transformation? It always takes the zero vector of the domain to the zero vector of the codomain. So image of the zero vector of V is the zero vector of W. Okay, this is always true for a linear transformation. Okay, fine. Now here is an exercise. So you are given a linear transformation T from R2 to R2 such that T of 2 comma 1 is this and T of 1 comma 3 is this. Now which of the following options are true, right? So here first of all, what is that you need to note? 2 comma 1 and 1 comma 3. Do they form a basis for R2?
Yes, ma'am.
So
Yes.
this forms a basis for R2. So whenever you find that you have the T defined for basis. So T is defined for basis means we can find T of x comma y for any x comma y in R2. Okay. So here it means what? You have to find what are the, how do we express x comma y as a linear combination of 2 comma 1 and 1 comma 3. So here I guess everyone knows how to do this, right? Is there anyone who don't know how to do this? Like finding this alpha and beta? Shall I straight away give you the answer or you want me to do the calculations?
Once do, ma'am.
Okay. So here what is that we are going to
Is
do?
the
Here
T of T of x comma y equal to alpha T of 2 comma 1
yes.
plus
After this, what you have to do is that you apply T on both sides. So you get alpha T of 2 comma 1 plus beta T of 1 comma 3. Then you know that alpha times T of 2 comma 1 is alpha times 3 comma 2. So 3 alpha comma 2 alpha and then T of 1 comma 3 is 0. So this part is 0, right? So now how are we going to find alpha and beta in terms of x comma y? So for that, first look here. So here you have 2 alpha plus beta comma alpha plus
Plus 3 beta.
this is x comma y.
Y.
So 2 alpha plus beta is equal to x. Alpha plus 3 beta is equal to y. We are going to solve this equation. When we are solving this equation, so let us call this 1, let us call this 2. So first equation and second equation multiplied by 2. So 2 alpha plus beta is equal to x. And then 2 alpha plus 6 beta is equal to 2y. So suppose we are subtracting, then what will we get? Minus 5 beta is equal to x minus 2y. So beta is equal to
X minus 2y
minus
by
x minus 2y by 5. Okay. So now from this, how do you find alpha?
Substitute back.
Yeah. So alpha, 2 alpha plus beta. So beta is minus x. So substitute in 1. 2 alpha minus x minus 2y by 5 is equal to x. So 2 alpha is equal to x plus 2y by 5. So 5x plus x is 6x plus 2y by 5. So now you have 2 on both sides commonly. So you can cancel out and get 3x plus y by 5. So you have found alpha and beta, right? So now you know what is alpha and beta. Now how do you write t of x comma y? Only alpha is needed here. So t of x comma y is nothing but 3 times of 3x plus
X
y
plus
by
Y.
5, 2 times of
3x
3x plus y by 5. So this is 9x plus 3y by 5, 6x plus 2y by 5. Correct?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so here I made a mistake, I guess. So this is x minus 2y, right?
Yes, ma'am.
Oh,
The beta is equal to minus x plus 2.
So 6x minus 2y, so 3x minus 5. So 6x minus 2y. All right.
9x minus 3y.
9x, yeah. Right? So let's compare t of x comma y, 9x minus 3y, 6x minus 2y by 5. So this is the expression, right? So obviously you can see that this is not a linear transformation. What is the general format for t from R2 to R2?
ax plus by.
So what is the general format? T of x comma y is equal to general format.
A
What is that?
times
Ax
alpha 1
a1x
x
plus
plus beta 1
b1y,
y
comma
a2x plus
x plus beta 1.
b2y. So you see that this option is not in this form at all, right? There is a 1 here, right? It is not in this form. So straight away you can say that this option is incorrect. This option is definitely of this form. So we have to check whether it satisfies. So t of 2 comma 1, does it satisfy this condition? T of 2 comma 1. So you are getting 2 means 6 here, 2. So you are not getting this. So you can say that this is also incorrect. And for the fourth option, I have mentioned that. So if t is defined for the basis, we can definitely find what is t of x comma y. So this option is also incorrect. Okay. And we have verified that this option is correct. All right. Okay. Clear?
Yes, ma'am.
Ma'am, please
Yeah.
fourth option again.
See, fourth option, it is saying that t cannot be determined from the given information. But what I said is that if you see that t is defined for the basis, then we can always know that this is the process for finding the t of x comma y. So here they are saying we cannot find, which is incorrect. Okay.
Yeah.
Oh.
Ma'am, I'm sorry to interrupt. I'm just stuck in this particular, ma'am. Txy is equal to alpha t2 comma 1 and then beta t 1 by 3, 1 comma 3. Ma'am, after that I couldn't.
See, here I am
get it.
applying t,
Can you just
applying
repeat?
t on both sides.
Right, ma'am.
So t of x comma y and t of this entire term. And since t is linear, I can split this.
Right, ma'am.
So first t of this is u plus v. So t of u plus t of v. And then t of alpha times of this vector. So alpha I can bring out. So I have just used the property. These two properties I have used here to get this. All right.
After that, ma'am, how you calculate, ma'am?
T of 2 comma 1 is given as 3 comma 2.
Okay.
And t of 1 comma 3 is 0 0. So only you have 3 comma 2 here and this part becomes 0. So alpha times of 3 comma 2 is 3 alpha comma 2 alpha. Clear?
Oh, okay, ma'am. Okay.
Right? Okay. So is this clear for everyone, this problem?
Yes,
Yeah?
ma'am.
Yes, ma'am.
Okay, let's
Yes,
move on
ma'am.
then. Okay, so here I have given the general steps. So if you are given a linear transformation T from Rn to Rm, where you are given the images of the basis of V. Here V is Rn. Okay, if you are given the basis of images of basis of Rn, then what is that you need to do? You take the basis V1, V2, Vn, which is given here, right? And you take a random vector from the space Rn. You take this V as linear combination of these vectors, basis vectors, and you need to express each of these coefficients in terms of x1, x2, xn. Exactly, that is what we did here, right? We wrote this general vector x comma y as a linear combination of the given basis vectors, and then we found alpha and beta in terms of x and y, right? In terms of x and y. And then we apply t on both sides, substitute the values of t of vi. T of vi is what is given to you. You substitute that, simplify, and find the expression for t. Got it? Right? Okay. So what are the types of linear transformation? Injective, surjective, and bijective. So what is a injective linear transformation? So that is a
1, 1.
one-to-one map. So
One to
T of
one.
V1 equal to T of V2 should imply V1 equal to V2. Or the usual way of saying is that if T of V equal to 0, then V is equal to 0. What does this condition says? If
T
T
of
of V
0
equal to
should be
0, what does it say
Kernel of
about
T
the
equals to 0.
kernel of T?
Only
Kernel of
zero.
T equals to 0.
Always has a 0. Trivial solution.
So whenever you have
Singleton
1 to
0.
1, you know that kernel is singleton 0. And the next one is surjective map. It means that for every W in W, there exists V in V such that TV is equal to W. Right? And what is the definition of the image of T? If you remember, what is the definition of image of T? I guess I have written it here. So it is a set of all W in W such that TV equal to W for some V in V. Now it is given that for every W in W, there exists a V in V such that TV equal to W. It means what? It means what? Your image is
It is
entire W.
yes,
Subspace.
entire codomain.
Yeah, your image is entire codomain. So this means that your image of T, or sometimes you call it range of T, both are same, is nothing but your codomain W. Right? And what is an isomorphism? If it is both one-to-one and onto, then we say that T is an isomorphism. In that case, you have both kernel 0 and range is W. Right? So now from rank nullity theorem, what will you get? So rank nullity theorem says that rank of T plus nullity of T is equal to
N.
dimension of V. Right? Now rank of T is nothing but the dimension of range, right? So which is dimension of W, and nullity is 0. So what do you get? If T is an isomorphism,
Dimension of V equals to
Dimensions of
dimension of
V
W.
and
dimension of V and W are
equal.
same. Okay, fine. So we define two vector spaces V and W are isomorphic to each other if and only if there exists an isomorphism T from V to W. Okay, and any n-dimensional vector space is isomorphic to which space? Rn.
Rn.
Okay, so there exists an isomorphic linear transformation T from V to W if and only if dimension of V equal to W. So either way it is true. So if you know that there is isomorphic transformation from V to W, then dimension is same. Also, you know that if the dimensions are same, then you can find a linear transformation such that it is isomorphic. Okay, fine.
Yes, ma'am.
So
Ma'am,
here, just giving an example here. So let me take maybe this example where you have, I guess we have seen this example, some similar example yesterday. A, B, C, D, A plus B is equal to 0, C plus D is equal to 0. First of all, is this a subspace?
No.
Yes.
Huh?
Just think about it. Is this a subspace or not?
No, the zero vector doesn't exist.
Why? The zero vector, if you
It's
put,
a
take the zero
subspace, man.
matrix, the sum is 0, right? The
It's
example
subspace.
we saw yesterday was A plus B is equal to 1 and C plus D is equal to 1. That's why zero
Yes,
vector
yes.
was not there. But here you see A plus B is 0 and C plus D is 0. So now this is a subspace, right?
Yes, ma'am.
And you
Yes,
can
ma'am.
rewrite this as
A
A
minus A
minus A, C
minus C.
minus C. A and C in R. So now, what is the basis for this space?
1 minus 1, 1 minus
1
One
minus
minus
1,
0,
0,
0.
0,
0, 0.
and
0, 0.
0, 0,
0,
1,
0,
1 minus 1.
1 minus 1.
one minus
Right? So now you know that this is a basis. So what is the dimension of this space? Let's call this
two.
W. What is dimension
2.
of W? 2.
2.
2.
Okay. So from this you can say that this W is isomorphic to which space?
R2.
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 Is isomorphic to R2. Right? Now let us maybe say you have another space, maybe W1, which is set of all x comma y comma z, such that x plus y plus z is equal to 0. Now what is dimension of W1?
2.
2.
Again, it is true,
3.
right? It is a two-dimensional space. It is actually a plane. So it is two-dimensional. So this is also isomorphic to R2, and also W is isomorphic to W1. Both are having same dimensions, right? So these two are also isomorphic. Okay. All spaces which are having same dimensions according to this condition. So all spaces of same dimension, they are also isomorphic. Okay. Clear?
Yes. Yes, ma'am.
Okay.
Yes,
Fine.
ma'am.
Yes, ma'am.
So next we move on to week 6 topics. So in week 6, so first we see what is kernel. So kernel or null space of a transformation is nothing but the set of all V in V such that TV is equal to 0. We know that this is a subspace of V. And image or range of T is nothing but the set of all W in W for which you have a pre-image in the domain. So this is also a subspace, right? And the dimension of kernel is called the nullity of T, and the dimension of the image or range is the rank of T. Okay. Now, what is the relation between injective map and nullity? We have already seen this. So, if a map is injective, it means that the kernel is 0, which means that nullity is
0.
0. 0.
And if you have a surjective map, that is an onto linear transformation, then you know that image of T is equal to W. If image of T equal to W, what can you say about the rank of T?
Dimension.
Rank
It is
Dimension.
equal to dimension of W, right? And if your T is a bijective map, you know that rank of T is dimension of W and nullity is 0. So from rank nullity theorem, you know that dimension of V is equal to dimension of
W.
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 So a for a linear transformation, if it is bijective, if and only if the dimensions are same. Okay, and one more condition. So if you have a linear transformation and you already know that the dimensions are same, then T is 1 to 1 if and only if onto. So it is, suppose you know that the dimensions are same and you know that already either one of this condition exists, then automatically the other one will also exist. So that is, let us say for example, if you know that T from R3 to R3. So both are having same dimension, domain and codomain. Okay. So suppose you know that T is 1 to 1. Then what can you say? T is also
On.
On 2.
on.
to.
Same way, if T is on to, then also you can say that T is 1 to 1.
1.
Okay. This statement is clear, right?
Yes, ma'am.
Yes,
Oh,
ma'am.
Oh,
Yes, ma'am.
Ma'am, what is identity transformation?
what is an identity transformation?
Yes, ma'am.
Okay. So what is an identity transformation?
Ma'am, can you repeat the statement again, ma'am? Just what you said.
Okay, for a linear transformation T from V to W, okay, so you have a linear transformation T from V to W. And you also know that the dimensions of the domain and codomain are same. dimension of V and W are same, then one of this condition, that either T is 1 to 1 or on to, will imply the other condition. You don't have to prove both. If you know that one of the condition is satisfied, then the other condition will automatically satisfy, right? Because you know that T is bijective if and only if dimension of V is equal to dimension of W, right?
Yeah.
And already if 1 to 1 is there, then you can automatically see that it is on to. From Rank-nullity theorem, you can easily prove this. All right?
Okay. Okay, ma'am.
Fine. So someone asked, what is an identity transformation? So for an identity transformation, you should have the domain and codomain to be the same. Then I of V is equal to V. This is the identity transformation.
Okay, ma'am.
Okay, fine.
Okay.
Okay, so look at this question. So if T is a one-to-one linear transformation, if and only if there does not exist any non-zero vector such that T be equal to 0.
True.
True, right? Because if T is 1 to 1, you know that kernel of T contains only the 0 vector. It means what?
Yes, ma'am.
Kernel is not having any non-zero vector. That is what is given here. So it is true. Correct?
Yes,
Yeah.
ma'am.
If
Yes.
T from R2 to R2 is a surjective linear transformation, then it cannot be injective.
False.
False.
False, because that is what we saw here, right? If T is from R2 to R2 and T is on to, then automatically T is 1 to 1.
1 to 1.
So this is incorrect. Here, if T from R to R is a linear transformation which is not injective. Not injective means what? Your kernel of T
Has more
contains
than
some non-zero vector.
0.
Nullity goes to 0.
There exists V not equal to 0 such that V belongs to kernel of T. Right? So you have TV is equal to 0. Now, what is the general form for T from R to R? So T of X is equal to
0.
Alpha X.
How about 0?
Ma'am, you're on mute.
Ma'am, no voice.
Ma'am, your voice got broken, ma'am. Not coming.
Ma'am, your mic is off.
Am I audible now?
Yes, ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, fine. Okay. So, sorry, I don't know what happened. Suddenly, I was not audible. Okay, let's continue. So, till which part were you able to hear me?
T of X equal to
Option
alpha
number
X, ma'am.
3.
Okay, so let's start with option number 3. So you have T from R to R is a linear transformation which is not injective. Then T must be 0. So is this statement true? For this, first of all, it is
False.
given that T is not injective. What does that mean? So you have a non-zero vector in kernel, that is TV is equal to 0 for some non-zero V. Now what is the general form for T from R to R? T of X is equal to
Alpha.
Alpha.
X.
now TV
X.
is equal to alpha V, right? And this TV is already 0 and V is non-zero. What does that mean?
It's not an
Alpha.
integer.
Alpha equal
Alpha must
to
be 0.
Alpha is 0,
Yes.
right?
Yeah.
It means what? Your T of X is equal to 0 for all X in R. So it means this is the statement given to you, right?
Yes, ma'am.
Yes, ma'am.
So this option is correct.
Correct.
Yeah. If there exists some non-zero vector V in V such that TV is equal to 0 for a linear transformation T from V to W, then T cannot be an isomorphism. So what does this first part tell you? This first part tells you that
T of
kernel is
kernel equals to 0 for some non-zero.
non-zero.
Oh, sorry,
No.
zero.
Yeah.
Because there
It
exists a
cannot be
non-zero vector.
injective.
So this means that T is not 1 to 1.
Mm.
So if it is not 1 to 1, it cannot be an isomorphism, right?
Yes.
Yes, ma'am.
Yeah. Okay then. Okay, so this problem is clear for everyone?
Yes, ma'am.
Yeah.
Yes, ma'am.
Actually, how
I'm
you
actually
conclude?
third option is
That's what I tried to say.
not clear, ma'am.
Which
Third
part you
option.
have now?
Third
Option 3.
Yes, ma'am.
I
General form.
understood
Th-
up
th-
to
Okay,
third
maybe I'll
option.
explain
Third
option 3 again. Okay.
option.
okay.
So option 3, you are given a linear transformation T from R to R. And it is given that T is not injective. Right? T is not injective means what? Your kernel of T is not just 0.
Not empty.
Yeah. So this means that there exists V non-zero such that TV is equal to 0. Right? Now what is the general form for T from R to R?
T of X is equal to alpha X.
Right? So this is the general form. Now let us see what is TV then.
Alpha V.
TV is alpha V. But already we know that TV is 0. Okay. Now V is non-zero. So this should imply
Alpha is equal to
Alpha is equal to 0.
Alpha equals
to 0.
I is
So
0.
you have T of X is equal to 0 for all X in R.
okay.
Right? So this statement is correct. T must be 0. Okay? Clear?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. Okay, so what is a matrix representation of a linear transformation? Okay, so you have a linear transformation T from V to W. So this is an important part of this week 6. So please pay attention. So T from V to W is a linear transformation. So you should have a basis for the domain as well as a basis for codomain to write the matrix representation. So here are two bases which is given for V and W. Okay. Now you are going to write each of these basis elements of the domain, okay, as a linear combination of the basis elements of the codomain. So each of this V1, V2, Vn, you are writing the images as a linear combination of W1, W2, Wn. Then how do you write the matrix? So here you write the coefficients of T of V1 in the first column. Then you write the coefficients of T of V2 in the second column. Then you write the coefficients of T of Vn in the third column. Right? This is the usual procedure to write the matrix representation of a linear transformation. Right? So let us look at a simple example for this. You have T from R3 to R. By the way, here if you have T from V to W, what will be the size of the matrix representation? So
Row
suppose
of
you
V.
say that dimension of V is n and dimension of W is m.
M cross N.
M by N. Size of T
M
is
by
M
N.
by N.
M times N.
Right? Okay. So now if T from R3 to R2, then the matrix A should have size
2 into 3.
2 cross T.
Okay. So first of all, they are asking the matrix of T. Straight away, you look at the size of the matrix. What is the size of this matrix?
3 cross 2.
3 cross
So
2.
this cannot be an option first of all. That we can easily see. So we have to check whether this matrix is correct. So it first of all satisfies the condition that it is a 2 by 3 matrix. But we have to check whether the entries are correct. So here we are, whenever you are not given any basis, it is assumed that we are considering the standard ordered basis. So what is the standard ordered basis for R3?
1
1
0
0 0
0
0 1 0
0 0 1.
0 1.
And for R2 it is
1
1
0
0
1, 0, 0, 1.
0 0, 1.
So what is T of 1, 0, 0 for this transformation?
1.
2 comma 0 0
2,
2, 0.
0,
1.
0, 1, 0 means you will get
1 comma 0
1,
1,
0.
comma 0
So T of 0, 0, 1 is
0 comma
0
1
0, 1.
right. So you can see that if you call this as maybe V1 and V2, then you can see that this is 2V1 plus V2. This is V1 plus 0 V2. This is 0 V1 plus V2. Correct?
yes
Yes,
ma'am
ma'am.
So you see that now if you are expressing the coefficients of T, maybe let's call this as W1, W, maybe I should have written it the other way around. Let's call this as W1, W2 and this is V1, V2.
Ma'am, 2v1 plus 0 v2, right?
Oh, sorry, 0 V2. Sorry. So this is W1 and W2. W2, W1, W2, W1, W2. Okay. So here you see that T of V1 is 2, 0 and T of V2 is 1, 0 and T of V3 is 0, 1. Clear how we got this matrix?
yes
Yeah.
ma'am
Yes.
So this option is
Yes,
correct.
ma'am.
Ma'am, can
Sorry
actually
for writing it in a clumsy way. Yeah.
actually, ma'am, sorry, my network got lost, ma'am. Can you repeat, ma'am, just this particular, ma'am, matrix representation, ma'am?
Yes. So here you see that we have to write the matrix of T by writing this images of the basis of the domain as a linear combination of the basis of codomain. Okay. So here these are the basis of codomain. So the images, these are the images which we have found. So we have to write them as a linear combination of this. So you get 2W1 plus 0W2 and then 1W1 plus 0W2 and then 0W1 plus 1W2. So now the coefficients, we are writing it as columns. So coefficients of TV1 are 2 and 0. Coefficients of TV2 are 1 and 0. Coefficients of TV3 are 0 and 1. Clear?
Okay, ma'am.
Sorry to interrupt, ma'am.
Yeah.
Ma'am, can you please just clarify how you got the images?
I have just substituted 1, 0, 0 in place of x, y, z.
Okay. Sorry, ma'am. Thank you.
Okay. So a basis for the null space of T is 1 minus 2, 0. So now what is a basis for null space? For that you should know what is the null space, right? So null space means you should have T of x, y, z is the 0. So 0 means 0 in R2, right? So it means you should have 2x plus y, z to be 0, 0. So this means that 2x plus y is 0 and z is 0. And this means that your y is minus 2x, right? So what is your null space or kernel of T? Kernel of T is nothing but set of all x, minus 2x, 0. Do you agree?
Yes, ma'am.
Yes, ma'am.
So what is the basis for x, minus 2x, 0?
1 minus 2 0.
1 minus 2 0.
Yeah, 1 minus 2, 0. So that is what is given here. So the basis, so this is having dimension 1, so it cannot have 2 elements in the basis, right? So this option is incorrect. What is the basis for the range of T? How do you find the range of T? So for finding the range of T, if you have the matrix, you don't have to worry about anything. So just look at the matrix. Okay. So now you know that the columns are nothing but elements of R2. Correct? So the columns are the elements of your codomain. So you have to just look at what is the column space of your matrix that gives you the range of T. So what is the column space of this matrix? Can you tell?
Span of the columns.
So here, yeah. So column space of A. So first of all, range of T is nothing but the column space of A. And here column space of A is spanned by which vectors? What are the linearly independent vectors you can say from this?
1,
0,
0, 0, 1.
2.
So you can say 1, 0 and 0, 1. And this gives you entire
R2.
R2. So if you take any two linearly independent vectors in R2, that will be a basis for the range of T. True or not?
Yes, ma'am.
So it means if instead of these vectors, if you have any two linearly independent vectors, then it is going to be a basis for range of T. Correct?
Yes.
So here this is also a linearly independent set in R2. Hence this is a basis for range. Clear?
Yes, ma'am.
So this is obviously incorrect because only one vector is there. Okay, so this problem is clear for everyone?
Yes, ma'am.
Yes, ma'am.
So the next question here is that you are having a transformation from
Hello,
R3.
ma'am.
Yeah.
Ma'am.
Yeah.
Ma'am, please option 5 again.
Option 5. See, we
Ma'am,
have to
column.
find. Okay, so range of T. How do you find range of T? So from the definition of range of T, you can find what is the range. This is one way of doing. But whenever you have a matrix, you don't have to worry about this definition because you have a easier way. So range of T is nothing but the column space of A. Why is that so? See, the rows are from domain and the columns are from codomain, right? And your range is a subspace of codomain, right? So you need to consider the column space of A. Okay, fine.
Yes, ma'am. Yeah.
So column space of A is nothing but the span of the linearly independent columns, so which gives you R2, and this also is a basis for R2, and hence this option is correct. All right?
Yes, ma'am.
Okay. Okay, so we are having a linear transformation T from R3 to R3. Okay, so this is a general linear, general form is given. So from the general form, the matrix representation is given. Now, can you tell me what is the basis with respect to which this matrix is formed?
1, 0, 0.
The standard ordered basis, right? So they have considered the standard ordered basis for obtaining this matrix. Yes. Now the question is, so which of the options are correct? T is injective if and only if the system of linear equation AV equal to 0 has a unique solution. True or not?
True, ma'am.
True.
So in fact, this is the definition, right? The kernel should be singleton 0.
Yes,
Okay.
ma'am.
Unique solution means you know that V is equal to 0, right? So AV is equal to 0 implies V is equal to 0 means this is 1 to 1.
Rank is full, nullity is 0.
Yeah, there are several ways to interpret it. Yeah. So T is injective if and only if rank of A is 3.
Yes,
Yes, ma'am.
nullity.
True.
Yes, because T
Yes.
is injective tells us that nullity of T is 0.
Nullity is
So
zero.
from rank nullity theorem, you know that rank is 3.
3.
Where the domain is having dimension 3, hence rank is 3. Okay, so this is also correct. If the system of linear equation AV equal to B for any B in R3 has a solution. First of all, this is nothing but the definition of
Homogeneous.
Homogeneous.
this is So the full statement you have to consider. So
On
AV,
to.
AV equal to B has a solution for any B in R3. So this is the definition of onto, right?
Onto.
So then T must be surjective. So they have just given the definition. So of course this is correct, right?
Yes, ma'am.
So instead of giving T, they are giving in terms of A. That's all. So here this statement is correct. Do you agree?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Sorry. Here.
Since it is from the same dimension and injective, it implies
again?
surjective.
Sorry, what was the question here?
Ma'am, can you please explain this option again?
Okay, option 3
number
I'll explain. So option 3, see what is mean by T being onto? What is the definition of T is onto? So for every W, so suppose you have T from V to W, then for every W in W, there exists V in V such that TV is equal to W. Correct? Yeah. Now, instead
Yes,
of
ma'am.
this statement, now they are saying for every B in R3. So instead of W, they are using B, and instead of this capital W, they are using, what is your capital W here? R3. They are saying that AV equal to B has a solution. What does it mean by saying AV equal to B has a solution? It is same as saying there
Onto.
exists a V in R3 such that AV equal to B. Correct? AV equal to B has a solution means what? There exists a V in R3 such that AV equal to B. True or not? Understood
Yes,
or not?
ma'am.
Yes,
So
ma'am.
the
Yes,
same
ma'am.
statement they are giving in terms of A instead of T. That's all. Okay. So instead of V, it is R3 here. Clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So what is the statement 4? Option 4. So if T is not surjective, okay, if it is not surjective means this statement, how does it change? For some W in W, you cannot find a pre-image, right?
Yes.
So say the same statement, how it will change in the case of matrix? For some B, AV equal to B has no solution. Correct? So the same is given here. For some B, AV equal to B has no solution. Okay?
Yes, ma'am.
So this option is also correct. Is this clear for everyone?
Yes, ma'am.
Yeah?
Yes, ma'am.
Okay. Okay, let T from R2 to R2 be a linear transformation such that T of x comma y is equal to x comma 0. Is T 1 to 1 or on to? So there are two ways. One is just look at the transformation, find the kernel or image. Other one is just look at the matrix with respect to standard basis. Can you quickly tell what is the matrix with respect to standard basis? T
1,
of 1,
0.
0 is?
1, 0, 0.
1, 0.
T
1,
of 0,
0,
1
0.
is?
0,
0,
0.
0,
So the matrix
0.
is nothing but 1, 0,
0,
0,
0.
0.
Kernel is not 0.
Not
So
1, ma'am.
what is the determinant of A?
0.
0.
0.
So or you can
0.
straight away also look at
Rank
the
is
rank. Rank is 1 and
1.
nullity is also 1.
1.
1.
So it
Not 1,
means
1.
it is not 1 to 1 and not
Onto.
Even not to.
so neither 1 to 1 nor on. Clear?
Yes,
Yeah.
ma'am.
Yes, ma'am.
So the
Yes, ma'am.
same way, can you quickly tell for this problem as well? What is T of 1, 0?
1,
1, 1.
And 0,
1,
1?
0.
1, minus
1,
1.
minus 1.
So your matrix is 1, 1, 1
1,
minus.
1, 1 minus
So
1.
what is the rank of A?
2.
You have two linear independent column. So rank is 2. Right? Two linearly independent column, rank is 2. So if rank is 2,
Nullity
what is
is
nullity?
Nullity is 0.
0.
0.
So you see that T is
Isomorphism.
yes isomorphism, both 1 and on 2, and hence it is an isomorphism. Clear?
Yes, ma'am.
Okay. If the matrix corresponding to a linear transformation with respect to this standard ordered basis for both domain and codomain is given like this. So which of the following is appropriate definition of T? So how will you find? So it is given that T of 1 0 is 2 comma 1. T of 0 1 is given as 3 comma 4. So T of x comma y is
2x
x times 2 comma 1 plus y times 3 comma 4. So 2x plus 3y
Ty
x plus
now x
4y.
plus 4y.
So this is one way. The other way is that you simply multiply 2, 3, 1, 4 with x comma y. See, remember, this can be done only when you have the standard ordered basis. That's why I did not give this straight away, because if the underlying basis is different, then you need to write this x comma y as a linear combination of the basis given to you. Okay, here it is standard ordered basis, so you don't have to think much. Straight away we can write. If it is a different basis, then you have to first of all express x comma y as a linear combination of these bases and then perform these operations. Okay, so also since it is standard ordered basis, you can also straight away find it in this way: 2x plus 3y, x plus 4y. Sorry, 2x plus 3y, x plus 4y. Yeah. So which option matches with this? 2x.
4.
Yeah.
Option 4.
So is this problem clear for everyone?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So is this T 1 to 1 or on 2? What is the rank of this matrix? So let's call this A. What is rank of A? You see two linearly independent columns. What does this mean?
2.
Rank is 2. And what is nullity?
0.
Nullity 0.
So this means that T is both
1
On
and
1 and on 2.
Isomorphism.
right? Okay. What will be the matrix representation of T with respect to beta for W and gamma for R2? So beta is this, I guess. So this is beta and gamma is this. Okay. So now what is that you need to do? So let's
apply the
call
transformation in 2x plus 3y comma.
yeah. So you call this V1, V2 and you call this as W1, W2. So what is T V1 first of all?
W1.
So we have already found it 2 comma 1. Now how will you express 2 comma 1 as a linear combination of W1 and W2? So here you need to find alpha 1 1 comma 1 plus beta 1 1 comma minus
1 comma minus 1.
Same way
Alpha plus beta is 2.
TV2 we have already found it to be 3 comma 4.
3 comma 4.
Now you need to express 3 comma 4 as a linear combination of W1 and W2. So alpha 2 times of W1.
Here we use the standard basis for beta, ma'am.
For what?
For beta, we have used the standard basis 1001.
For beta.
Yes, ma'am.
What do you mean by for beta? Okay, so here beta is this basis.
Yes, ma'am.
What was your question? Did I answer it?
Yes, ma'am. I was asking that the beta is 1001. The base is beta.
Yeah. Okay, so now you see that let us call this matrix representation of T with respect to beta and gamma as maybe B. So what are the entries of B? Can you tell? Alpha 1.
Alpha 2.
Here what should be the entry?
Beta 1.
Alpha 2, beta 2.
Beta.
So finding this alpha 1, beta 1, alpha 2, B2 are just solving system of linear equation. Can I leave it to you as a homework?
Yes, ma'am.
Yes, ma'am.
Okay, so this part I can leave you. Find alpha 1, beta 1, alpha 2, beta 2. So this is a homework for you. Just some simple homework. Okay, fine. Okay. So next you have the linear transformation. So this problem is clear for everyone, right?
Yes, ma'am.
Yes, ma'am.
So consider the linear transformation T from R3 to R2, T of x comma y comma z is 2x plus 3z, 4y plus z. Now find the null space of T. How do you find the null space of T? So
T
you
of
should have T of x comma y comma z is 0.
that is 0
So 2x plus z, 3z, comma
equal to
4y plus 3, 4y plus z should be 0, comma 0.
0.
Which
0.
means 2x plus 3z is
equal to
0.
0.
4y plus
4y
And 4y
plus
plus
z
z is
is
equal to 0.
0. Right? So you can write z as minus 2 by 3 x. And you can write y as minus z
minus
by.
Minus z 4.
So now z already know that you can write it as minus 2 by 3 x. Right? And then here you have a 4. So what is that you will have? X by
6.
6.
Right? So now your kernel of T or null space of T is nothing but x comma y is x by 6
X is 6.
and z is minus 2 by
Minus
3.
2x by 6.
So x and r. I hope I did not make any calculation error. Did you all just follow it along with me? There were no errors, right?
Yes, yes, ma'am.
Okay.
Yes, ma'am.
Okay, so now you know that what is the null space of T. Now from this kernel, can you tell me what is the dimension of this?
1.
1.
1.
So if dimension of nullity is 1, what is the dimension of this image? According to rank nullity theorem, you know that rank plus nullity is 1 is equal to 3. So rank
3.
should be
2.
2.
okay. Fine. So now
Ma'am,
choose.
I have one small doubt.
Yeah.
Instead of writing it in the x, we can write it in y or z.
That is up to your choice only. That there is no need to write it in terms of x or y. That is totally up to you. Okay, in fact, you can write in terms of z also. X as in terms of z, y in terms of z. That is actually convenient. Okay. So, yeah. So, is T an isomorphism?
No.
No.
Because nullity
No,
of
ma'am.
T is 1, this means that T is not 1 to 1, right?
Yes, ma'am.
It's only on.
Now, rank of T is 2. So, it means that rank
On
of
2.
T is same as dimension of R2.
W.
So, this means that T is on 2.
On 2.
On 2.
So T is on 2 but not 1 to 1 is the correct
1,
option.
1.
Okay. So this problem is clear for everyone? Yes, ma'am.
Yes, ma'am.
Okay. So here is an important statement here. So even without verifying, there are few facts which you can tell. So suppose you have T from Rn to Rm. Okay, this is a linear transformation. Then T cannot be on 2 if m is greater than n. Why? What happens if m is greater than n?
Rank is
So if m is greater than n and if T is on 2, then rank of T is equal to m.
Yes,
Then
ma'am.
you will have a contradiction to rank nullity theorem, correct?
Yes, ma'am.
Okay, same way, T cannot be 1 to 1 if m is strictly less than n. Why is that so? Nullity will be 0, implying rank of T is n. But rank of T
N.
is less than or equal to m. So this is not possible. Yeah. So here you see that if m is greater than n, then T cannot be on 2. And similarly, if m is less than n, then T cannot be 1 to 1. So in this scenario, m is less than n. So T cannot be 1 to 1.
1 to 1.
Okay, fine. Okay.
So, ma'am, we will never get a situation like R3 to R2 be bijective.
Yes, we will not get. We already know that it cannot be bijective from another statement that T from V to W is bijective only if the dimension of domain and codomain are same, right?
Okay, ma'am.
Yes, ma'am.
Yeah. Okay, consider a linear transformation T from R3 to R3 defined like this. Okay, and it is also given that ABC is not equal to 1. So this A, B, and C, the product is not equal to 1. So first of all, what is the matrix representation with respect to standard ordered basis? What is T of 1, 0, 0? 1 minus
1,
B,
minus B, 0.
T
Comma
of
0.
0, 1, 0 is A, 0,
A 0 1.
1.
and T of 0, 0, 1 is 0,
0 1 comma C.
So 1 minus B should come here, right? Here they have written the same along row, but you should have along column. See, this is something many students make mistake and get confused. Please remember, this column should represent TV1 column. Okay, column wise you should remember. TV2 should represent this column and TV3 this column. Right? Some of you get confused whether it is row or column. Okay, it is always the column. Please remember it. So option 2 is correct and option 1 is incorrect. Clear? Yeah?
Yes, ma'am.
Yes.
Okay. So now
Yes,
it is
ma'am.
given that ABC is not equal to 1. So how is this going to help us to understand the rank, nullity or basis? Okay. So can we look at what is the determinant? Let us call this matrix as A. Can you tell what is the determinant of A? Calculate quickly and tell me. 1 times of 0 minus 1 minus A times of minus BC plus 0. So you get minus 1 plus ABC. Right? And it is given that ABC is not equal to 1. So if ABC is not equal to 1, what can you say about this determinant?
Determinant is not
No.
0.
Determinant is non-zero. What can you say about rank of A?
Rank is full.
Full rank.
Rank is full rank.
3.
Right?
3.
So rank is 3. So rank is 3 means a basis for range of T is
Yeah.
1 0 0 0 1 0 0 0 1 here actually.
0, 0, 1.
So is this correct?
Yes.
Yes,
Yes, ma'am.
Yes, ma'am.
A basis for the range, only 2 vectors are given, so incorrect. Rank
Incorrect.
is 2, incorrect. Rank is
Incorrect.
3, correct. So if rank is 3, nullity is?
0.
0.
0.
So this problem is clear for everyone?
Ma'am,
Yes,
Yes.
can you
ma'am.
explain that not equal to 0 part that?
Which one? This one.
Yeah.
So it is given ABC is not equal to 1. So this means that ABC minus 1 is not equal to 0. So ABC minus 1 is not 0. Okay?
Yeah, got it.
Okay.
One more thing, ma'am.
Yeah.
Can you explain the option 4?
Option 4.
Yes, ma'am.
See, now the rank is 3. Rank is 3 means the range should have dimension 3. So range should have dimension 3 means how many elements should be there in the range of basis for range of T?
3 elements.
So can option 4 be correct?
No, ma'am.
So is this problem clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay,
Yes, ma'am.
then we'll move on to the next week. So week 7. So week 7, the number of topic is actually very less. Only 3 topics exactly. So equivalent matrices, similar matrices, affine spaces. Only this much you have in week 7. Okay. So here, the first topic, equivalence of matrices. So 2 matrices A and B. So equivalence of matrices is for any rectangular matrix. So both the matrix, first of all, should be of the same order. We call it to be equivalent if there exists invertible matrix P and Q such that B is equal to QAP. Okay. So we have seen in our live sessions of the week 7 that this is an equivalence relation. And I'm not going to explain this part and all here. Okay. This is already explained completely. I'm not going to explain, but you should know that this is an equivalence relation. Okay, fine. And how do you find P and Q for this particular case, what is the particular case? So if you have a linear transformation T from V to W, and you have two bases for the domain and two other bases for the codomain. So A is a matrix representation with respect to beta 1 of V and gamma 1 of W. And B is a matrix representation of T with respect to beta 2 of V and gamma 2 of W. Then we say that A and B are equivalent. Okay, so in this scenario, A and B are equivalent and it satisfies the equality B is equal to QAP. And this P and Q are specifically given in this way. So how to find this P and Q? Again, I'm not going to explain. Please refer to our live session videos. Finding this P and Q, it is time consuming. So please refer to the sessions. Okay. By the way, this is something important. You should know that this part, that if you have such linear transformation and two different matrices representing the same transformation, then they are equivalent. This part you should definitely know. For example, here I guess we did some example. Where was that? Yeah, this one. So this is a transformation with respect to standard order. This is a matrix with respect to standard ordered basis, and this is a matrix with respect to some other basis. So what can you say about the relation between A and B?
Equivalence.
Yeah. So here A and B are equivalent. So now without even knowing what is B, okay, without even knowing what is B, can you say what is rank of B?
2.
Yeah.
Rank of B is 2. Why is that so?
Same as
Because
the rank
if
of
matrices are
Because
equivalent,
equivalent.
then the rank of the matrices are equals.
equal.
Okay. So if two matrices are equivalent, then the rank of the matrices are
Should be
equal.
same.
Okay. And also the other property is that A and B are equivalent if A can be transformed into B by a combination of elementary row and column operations. So usually this is the main property which we are using, the rank property. Very rarely we use this property as well.
The
Okay.
only thing to look for is the ranks, right? If the rank
What?
are equal, they are equivalent.
Yeah. If the rank are equivalent, then the matrices are equivalent. Okay. Of course, the matrices should be of same size. That is the first thing. So here you see these two are matrices of size. What is the size of these matrices?
2 cross 3. 2
Yeah.
Two
cross
cross.
2 cross 3 matrix. And what is the rank of A and rank of B?
2.
2.
2.
You see these two rows are linearly independent. So rank is 2. Again, these two rows are linearly independent. So rank is 2. So they are equivalent. Okay. I guess here something got pasted by mistake, I guess. So here you should have, I guess the question was with some 3 cross 3 matrix, I guess. 3 cross 3 or 3 cross 2, I don't remember. Yeah. So suppose you have a 3 by 3 matrix and matrix B like this. Let us say rank of A is equal to rank of B. Are these two matrices equivalent?
No.
No.
No, ma'am.
A and B are of different size. Right? Different
A
size.
can,
So
B
not
cannot be obtained in the form of A.
Yeah. Okay. So the next concept is similar matrices. So two matrices A and B of order n by n are said to be similar if there exists an invertible matrix P such that B is equal to P inverse AP. Okay. So earlier we had QAP. Now we are having only one matrix P and the inverse of it. So B is equal to P inverse AP. Okay. So now for similarity of similar matrices, it is obvious that if two matrices are similar, then they are also equivalent. One thing you should remember, similar matrices are defined only for square matrices.
Square matrix.
Only for square matrices. Okay, fine. And also similar, if matrices are similar, then they are also equivalent. This is again something important. Okay. What about the converse? The converse is not true. So it
May
means
not be.
that equivalent does not imply or need not imply similarity. Okay, so here is an example. these two are not similar. Why they are not similar?
A tray. Sorry.
What
Determinant
does
not.
it mean by A and B to being similar? If
Trace, rank, and determinant.
B is equal to P inverse AP, if B is equal to P inverse AP, what will happen? Your A is nothing but identity.
Here it is not
So
similar
P
because
inverse
it is
AP
a
is going to be?
Identity.
Yeah. So this reduces to
Identity.
identity. But is B is equal to I?
No.
Not.
So this is not possible. So this means that this is not possible for any P. So A and B are not similar. Okay, in fact, the same type of argument can be given for any scalar matrix. So any scalar matrix cannot be similar to a non-scalar matrix. So it is similar to only itself. Okay, fine. So the similar process of finding A and B, the matrices P for a transformation T from V to B. Now you are having same domain. Remember, if you are having same domain and codomain, okay, and then you are having two bases beta and gamma for the domain and codomain. So A is a matrix representation with respect to beta for both domain and codomain, and B is a matrix representation of T with respect to gamma for both domain and codomain. Then what happens? A and B are similar. Okay, so here one thing you should note is that here for equivalence of matrices, this beta 1 and gamma 1, two different bases are used. But here you see that for similarity of matrices, this matrix is with respect to one particular basis and this matrix is with respect to another basis. So one matrix is corresponding to only one basis for similarity of matrices. Then A and B are similar and you can find P in the following way. Okay. So again, this what is the technique to find P? I'm leaving it to you to go through. Okay. But you should know that if you are having two matrices representing T with respect to one basis for one matrix, then you know that A and B are similar. Okay. So what are similar matrices and what are equivalent matrices? Is that clear to everyone?
Yes, ma'am.
Yes,
Okay.
ma'am.
Fine. So here are some properties of similar matrices. So if A and B are similar, then they have same rank, same trace, same determinant. But what about the other way around? So if rank is same, trace is same, determinant is same, can it imply that A and B are similar?
No, ma'am.
No.
No. Again, the
Not.
same example we can say.
Previous
What
example.
is trace of A?
2.
2.
What is trace of B?
2.
2.
What
2.
is the rank of A?
2.
2.
2.
What is rank of B?
2.
2.
2.
What is determinant of A?
1.
1.
What is
1.
determinant of B?
1.
1.
1. So all these are there, but
Still not similar.
A and B are not
You
similar.
know.
Okay. Fine.
Ma'am, if A and B are similar, so we can say nullity also similar. The same.
Yes, because rank is same, nullity is also going to be same. Yes. Okay. Fine. Let A be an n by n matrix which represents an isomorphism between two n-dimensional spaces. Okay, so it is representing an isomorphism. So if it is representing an isomorphism, what is the rank?
Full rank, I think.
N.
N.
And what is the nullity?
0.
0.
Okay. Now it is given that A and B are similar matrices. So someone also asked about nullity. So A and B are similar. Okay. Now nullity of B, can A be similar to a matrix B whose nullity is greater than or equal to 1? Is it possible?
No.
No, ma'am.
No, ma'am.
Right. So if A and B are similar, you know that. So if A is similar to B,
Then the rank.
Rank.
then nullity of A is equal to nullity of B.
Is it 0, ma'am?
Yeah.
Okay.
So the answer is no. Any doubts?
No, ma'am.
No, ma'am.
Clear, right? Okay.
Yes, ma'am.
So which of the following options are true? If A and B are similar, then A inverse and B inverse are similar matrices. True or not?
True.
Yes, right?
True.
Because if you can write B equal to P inverse AP, then take inverse on both sides. So B inverse equal to P inverse A inverse P. Correct? So you see that A
Yes.
inverse and B inverse are similar. So I have just taken inverse on both sides. So you know that inverse means the directions are reversed. So what is AB inverse? B inverse.
inverse
P
A.
inverse into A minus.
So I have just used this condition here. Okay. So you see that A inverse and B inverse are similar. Okay. What about option 2? If A and B are similar, then A square and B
In
square are
option A,
similar.
ma'am, they may
Yeah.
not be equivalent.
A and B are.
Not similarity implies equivalence.
Yes. See, no, he is asking A and B are equivalent, then A inverse and B inverse are equivalent.
ma'am.
That need not be true. Yes, that need
Yes,
not be
yes.
true. Okay, if A and B are similar matrices, then A square and B square are similar matrices.
Yes,
Again,
Yes.
the same technique only. So B square is equal to P inverse AP into P inverse AP. So when you simplify, you will get P inverse A square P. So this statement is also correct. In fact, instead of 2, if you have any k, then
By changing your mind with principle of mathematical induction.
sorry.
By using principle of mathematical induction.
Yes, you can do that. Okay, fine. What about option 3? The converse of the above
Here
statement.
also, ma'am, equivalent, like if A
Again,
and B are equivalent.
yes, we do not know about that for equivalent matrices. Yes. Okay. What about A square and B square similar implies A and B are similar?
No.
May
No, right?
not be.
Because for example, let us take your A square and B square to be in fact the same matrix. Now A is 1 0 0 minus 1, B is minus 1 0 0 1. Did I do it correctly, or maybe I should write 1 1 only? Now in this case, what is the trace of A and trace of B? Do they coincide?
No.
So if A and B
No,
are
ma'am.
not similar. Okay, so A and B are not similar. So option 3 is
Incorrect.
Incorrect.
And option 4, if A and B are similar matrices, then A transpose and B transpose are similar matrices.
True.
True.
Correct,
True.
ma'am.
True for
So
equivalent
you can
also.
again prove it in the similar way. Okay. So the next topic is affine subspaces and affine mapping. Okay. So what are affine subspaces and affine mapping? So before even going to the definition, just let us look at a simple graph. So here you look at R2. So you are in R2. So what does this red line represent?
Subspace.
Yes, this is a subspace, right? And what are these other two lines? They are parallel lines. Parallel to this. This is
Subspace.
also parallel. This is also parallel to this subspace. So let us call this maybe W. So parallel to W. This is also parallel to W. So whatever lines which are parallel to this subspace or the affine space corresponding to W. So both are. So now let's call this maybe A1 and A2. So A1 and A2 are affine spaces corresponding to W. Okay. Same way, if you are having planes parallel to a plane passing through origin, then those planes are affine spaces with respect to that plane. Okay, I don't have a picture here, but suppose let us say this is a plane passing through origin. Okay, so this is a subspace. So this is a plane through origin. And this is a parallel plane. So what can you say? This is a affine space. Okay, so this is an affine space and this is a subspace. Okay, so you understand how to imagine affine spaces, right? So they are kind of translation of the subspaces. Okay, they are just kind of shifted. That's all. From the origin. They are shifted from the origin. So they are affine spaces. So now what is the definition of affine space? So if you are having a vector subspace U and there exists a vector V in V, then this V plus U is your affine space L. Okay. So in this representation V plus U, this V is not unique, but your U, the subspace U is unique. Okay. So we have given several illustrations for why V is not unique and U is unique. So for those explanations, you can go through the session notes. Okay. Week 7 notes. Okay. We don't have sufficient time to look into every details here. Okay. I'm just telling you the main points here. Okay. So you can see affine spaces as translations of a vector subspace. Okay. So in fact, if you take V to be just 0, then you can see that in fact every subspace also is an affine space. Okay. And what is the dimension of the affine space? The corresponding dimension of the subspace is the dimension of the affine space. For example, suppose this is the affine space you are considering. What is the dimension of this affine space A1 and A2?
1.
1, because the dimension of this subspace W is 1. Same way,
1.
what is the dimension of this affine space L?
2.
2, because it is the dimension of the corresponding subspace here, right? So for affine spaces of R2, so what are the subspaces in R2? The 0 vector, any straight line through origin, and the whole space. So what are the translations of these subspaces? They are going to be the affine spaces in R2. So the point gets translated to a non-zero point, then 0 vector translated to a non-zero point. Any straight line through origin gets shifted to just any straight line, not necessarily through origin. Okay. And what about R2 shifting? R2, even if it gets shifted, it will still be R2 only, right? And what about in R3? In R3, the possible subspaces are 0 space, one-dimensional spaces, planes, and the whole space. So how will they get translated? The 0 vector to any non-zero vector, line passing through origin to any line parallel to that line, and planes through origin gets translated to planes parallel to the planes passing through origin and the whole R3. Okay. So how is addition and scalar multiplication defined for affine spaces? Remember, when you are doing addition and scalar multiplication, in that scenario, your V is going to be fixed. What does that mean? Suppose you take two different vectors from your L. We represent it as V plus U and V plus U dash. Then L plus L dash is nothing but V. You are keeping it as fixed plus U plus U dash. You do the addition only for the subspace part. Same way you do the scalar multiplication only for the subspace part. You keep the V fixed and do the scalar multiplication only for the subspace part. So addition and scalar multiplication on affine spaces, is that clear? Yeah?
Yes, ma'am.
Yes, ma'am.
Okay. Okay, so here are two affine spaces. L1 is this and L2 is this. Okay. Now it is given that W1, W2 are the corresponding vector subspaces of L1 and L2. So how do you find W1 and W2? So here you should remember that if so W is equal to set of all x comma y comma z such that ax plus by plus cz is equal to 0 is the subspace. Then what is the corresponding affine space? Is of the form x comma y comma z. Can you complete it such that ax plus by plus cz is sum d.
Sum d.
Okay, d in R. Okay. So if this is the affine space, then the corresponding subspace is this. And if it is this is the subspace, then the corresponding affine space is this. Okay. Now from this, can you tell me what are the corresponding subspaces?
W1 and W2, option 2 and option 3.
Option 2, x plus y plus 2z is equal to 0 and 2x plus y plus 2z is equal to 0.
Option 2.
Okay, so this is incorrect. This is incorrect. This is again incorrect. Clear? Yes?
Yeah.
Okay. Consider the affine space L1 and L2. So these are two affine spaces. Now again, yeah.
Ma'am, can you repeat the previous one, ma'am, once again?
See, if you are having the affine space as ax plus by plus cz equal to d, then the corresponding subspace is nothing but ax plus by plus cz is equal to 0. Okay?
Okay, ma'am.
That's all. So here instead of 6, whatever is having 0 for the same x plus y plus 2z, that is the subspace for L1. Similarly, 2x plus y plus 2z is equal to space for L2.
Fine, ma'am.
Okay. Now can you tell me what is W1 and W2 for this L1 and L2? So for what is W1 for this L1?
1
X plus
y plus 2z equal to 0.
Exactly. Okay, so this is your W1. So for this W1, how do you find a spanning set? How do you find the spanning set? How do you find the basis? Do you remember? How do you find the basis?
1, 0, 0.
So from this, what is the usual technique to find the basis for given subspace like this? No one remembers.
Writing
One
the
equal to 0, ma'am. variable.
dependent.
One Reduce equation. the variable.
Yes. So one variable you should reduce, right? So for example, z, if I am reducing, what will happen to z? Z is nothing but
Minus x minus y by 2.
By 2.
Yes, ma'am.
right? So this is how it reduces. Now, what is the basis you will get? X times 1, 0.
1, 0 minus 1 by 2.
Minus 1 by 2.
And
Y times
0, 1
1
minus 1 by 2.
0,
0,
1.
1
minus 1 by 2.
Minus 1 by 2.
Okay, so this is one way of doing. Here they have 1 minus 1, 0, 0, 1, 2. First of all, is this satisfying this condition? X plus y plus 2z is equal to 0. Is this
No.
satisfying? The first one satisfies. What about the
Yes.
second one? No,
No.
right? So this does not belong to W1. So this option is incorrect. So here basically they are saying W2 is the span of 1, 0, 0 and 0, 1, 0. Is this correct?
Yes, ma'am.
Is it standard form, ma'am? Standard basis.
Why they have taken W2 to be just a span of 1, 0, 0 and 0, 1, 0? I think option 2 is also incorrect, right?
Incorrect.
Yes,
Because
ma'am.
z is
That
3.
need not be that need not be 0 all the time, right? So this is also in. Oh, this is for W2. Sorry.
So
This
z is
not
3.
Okay, this is for W2. So first option is incorrect. It is fine. Now let us look at W2. So W2. So this is your L2. For this L2, what is your W2? So L2 is nothing but set of all x comma y comma 3. So what will be your W2 then? X comma y comma
3.
0.
0.
So that will be 0. Right? So z is equal to 3 plane they are considering. So z is equal to 0 plane we need to consider. So for W, this option is correct, right? Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. Now what is W1 intersection W2? So you should have minus x minus y by 2 equal to 0, correct?
0.
So it means x is
X
equal
equals to y.
x is equal to minus y, right? Yes or
Yes.
no? So x is equal to minus y. So does it represent a line passing through origin? So W1 intersection W2
That's y equals to
set
0.
of all
Yes,
x
ma'am.
comma minus x comma 0. X is in R. So this is definitely a line through origin, right?
Yes.
Yes.
So option 4 is incorrect.
Excuse me, ma'am.
Uh,
When the option 1, you said first element is correct. Can you explain why it is correct?
Which one is correct?
In the option 1, you said that first element is correct, second element is wrong.
Yes, yes, yes. So this is x, y, and z. What is x plus y plus 2z for this vector?
1 0 minus 1 by 2.
X plus y is 0. 2 times of z is 0. So this is 0. And what about x plus y plus 2? So let us call this x, y, and z. So what about x plus y plus 2z for this?
5.
0 plus 1 plus 4, which is 5. So this is not 0. For W1, x plus y plus 2z should be 0. So for the first vector, this is satisfied. So this belongs to W1, but this does not belong to W1. Clear?
Okay, ma'am. Thank you.
Ma'am, can you repeat option 3, ma'am, once again, ma'am?
Yes. What is W1 intersection W2? So W1 intersection W2, you see that these two places, the vectors are just the same. Only in the third place, the coordinates are different. So we are matching this third place coordinates in the third place. So x minus y by 2 is equal to 0. I'm doing. Okay. So then intersection means a point which is there in both W1 and W2, right? So it should satisfy the first form as well as the second form, correct?
Okay.
So it should be this as well as this. So both this should be equal. In that case, this reduces to x is equal to minus y, correct?
Okay, ma'am.
I am just writing it in this form. That's all. Clear?
Okay, ma'am.
Okay. So next, what is dot product? I guess dot product, everyone knows what is meant by a dot product.
Yes,
So dot product u1, u2, suppose you are having two vectors. So how do you do the dot product? So for example, 1 comma 2 dot product with minus 3 comma 1. What is the dot product?
1 minus 2.
1 into minus 3
plus 2
2
multiplied.
What is minus 3 plus 2?
Minus 3
Minus
2
1.
minus 1.
Okay.
Minus multiplication.
Yeah. And what is the norm of a vector?
Dot product with itself.
Root under
u1 square plus
Plus
u2
u2 square plus un square.
Okay, and what is the relation between this norm and dot product? Norm is nothing but square root
U
of
dot u.
u dot u, which is the same expression. Okay, and the formula for finding angle between two vectors. Suppose you are having two vectors. What is the angle between these two vectors? It is given by
Dot
this
product
expression.
divided by norm.
Yeah, cos inverse of u dot v by square root of norm u, norm v. Okay, norm u square, norm v square actually. So maybe just norm u, norm v. Square root and this square will get cancelled. Right? U dot v by norm u, norm v. Okay? Clear?
Yes, ma'am.
Okay. So inner product means a function from v cross v to r satisfying all this condition. Okay, so your inner product v comma v should be greater than 0 for all non-zero vectors, and it is 0 only for the 0 vector. And you can split the inner product in this way, and you can write it in the reverse order also. That will not change anything, and the scalar can be taken out. So if a function satisfies all this condition, then we call such a vector space with the inner product to be inner product space. Okay. And what is the norm on a vector space? Norm on a vector space is a function from a vector space to real numbers which satisfies these three conditions. The triangle inequality, and the second one is norm Cx is equal to mod C times norm x, and norm x greater equal to 0 for all x in V. And when is norm x 0? Only for the 0 vector. I'm kind of not explaining these things in detail because we have already discussed this in detail in the live sessions. Please refer to it if you have some doubts here. Okay, because we don't have sufficient time to look at all the details in the revision session. Okay, and how do we induce a norm from an inner product? Norm of V. So whatever is the inner product given, so you define it to be square root of inner product of V comma V. Okay, that gives a norm on V. Okay, so you can see that dot product is an inner product Okay, and the length of a vector defined in this way is a norm. Okay, fine. Moving to week 8. In week 8, the main topic is about orthogonal vectors. Okay, orthogonal vectors and orthogonal transformation. So what is an orthogonal vector? Two vectors. Yeah.
Angle between them is 90.
Yeah. So that is
product is 0.
when you consider dot product. But if you are considering any inner product space, then the definition is inner product u comma v is 0. So two vectors are orthogonal if inner product u comma v is 0. So a set of vectors is orthogonal if inner product vi comma vj is 0 for every pair of ij, where I is not equal to j. If every pair, the inner product is 0, then we say the entire set is orthogonal. Okay. Orthogonality implies independence. So this is a very important property. So this property says that if you have an orthogonal set, then this set is always linearly independent. So I'm not giving the proof here. So this statement is but anyway important. If you have an orthogonal set, then it is linearly independent. Okay, and what is meant by an orthogonal basis? A basis which is containing orthogonal vectors is an orthogonal basis. That's all. Okay, what about the standard ordered basis? Is it an orthogonal basis?
Yes.
Standard ordered basis, are they orthogonal with respect to dot product?
Yes, ma'am.
Yes, right?
Yes,
So
ma'am.
example of an orthogonal basis is standard ordered basis for Rn. Okay. So a basis, you know that it is a maximal linearly independent set, and orthogonal set of vectors, you know that they are already linearly independent. So what does that mean? So if you have dimension of V is n, then the orthogonal basis is nothing but an orthogonal set of n vectors. Okay. So if you take any orthogonal set of n vectors in an n-dimensional space, that will form an orthogonal basis. Okay.
Yes, ma'am.
Now, yeah. So what is an orthonormal set? Normal means just the norm should be 1. So if you have a set of vectors v1, v2, vn, first of all, it should be orthogonal and norm vi is equal to 1 for all I. If these two conditions are there, then such a set is called an orthonormal set. Okay. Same way, what is an orthonormal basis? Basis which contains orthonormal set. Okay. So it means what? Suppose you have a basis v1, v2, vn, and you know that the v1, v2, vn are orthogonal and the norm is 1, then such a basis is called an orthonormal basis. Clear? Okay. Fine.
Yes.
Each vector has norm 1 in an orthonormal basis, and an orthonormal basis is a maximal orthonormal set in the inner product space. Of course, basis is the maximal linearly independent set, right? Okay. So if you are given an orthogonal set, how will you convert them to an orthonormal set? So suppose let us say you are having 1 minus 1. What is a vector which is orthogonal to 1 minus 1? Can you tell?
Divide by root 2.
Yes, ma'am.
No. I'm asking an orthogonal vector to 1 comma minus 1.
1
Minus
divided
1
by
comma 1.
Ma'am, divide by its norm, ma'am.
How do you find in general?
x dot y equals
X
to
minus y is
So
0.
you should have x minus y equal to 0. It means x is equal to y.
1
Right?
comma 1.
So how do you
or 2
find an
comma 2.
orthogonal vector to a vector? So here, for example, 1 comma minus 1, an orthogonal vector is of the form 1 comma 1. Okay. So now you have two orthogonal vectors. So 1, v1, v2. So this is an orthogonal set. How do you convert it into an orthonormal set? You just divide it by its norm.
Norm. Root 2.
Here the norm is root 2 for both. Correct?
Yes, ma'am.
Yeah. Okay. So choose a set of correct statements. In an orthogonal set, the norms of all the vectors are equal. True or not?
Orthonormal.
Yes.
Yes, ma'am.
For orthogonal set, you don't know whether the norms are equal or not. Only in this scenario, the norms matched, but it need not be true that the norms are in general true. Only for orthonormal set, you know that each norm is 1. But for any orthogonal set, this is not at all true. Okay? So
Yes,
this
ma'am.
option is incorrect. In an orthogonal set, the vectors are linearly independent.
True.
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 In an orthogonal set, the vectors are linearly dependent. Of course,
False.
not.
False, ma'am.
False.
If the columns of an n by n coefficient matrix comprises the individual vectors of an orthogonal set in Rn, then there must be a unique solution to Ax is equal to b. When will we have a unique solution to Ax is equal to b? If the columns of A are?
Linearly independent.
Yes. So now, do we know whether the columns are linearly independent?
Yes,
Yes.
Yes, ma'am. True.
Yes, ma'am.
Orthogonality implies
Orthogonality implies
They are
independent.
linearly independent.
hence you can have a unique solution.
Yes, ma'am.
Okay. If the columns of an n by n coefficient matrix A comprises the individual vectors of an orthogonal set in Rn, then there are no solutions. This is kind of the opposite of this statement. So, of course, it's correct. The determinant of a square matrix formed by a set of orthogonal vectors in Rn is 0.
Incorrect.
False.
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 A set of n vectors can never form an orthogonal basis in Rn minus 1.
True.
True.
For Rn minus 1, how many elements can be there in basis?
N minus 1.
N minus 1.
And
N minus 1.
Minus 1 elements, right? Here they are saying n vectors are there in this basis. Is it possible?
No.
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 Obviously incorrect, right?
Yes, ma'am.
So all these options, yeah.
Could you give an example for that option 7?
Option 7. Okay, so just consider R3. Okay, so for maybe R2 also we can consider. So for R2, I'm going to consider the standard ordered basis 1 or maybe 1 0 0 1, and maybe I don't know some other vector I'm considering. I'm considering 3 vectors. Okay, I'm considering 3 vectors. Can this form an orthogonal basis in Rn minus 1?
No, ma'am.
No.
This is not an orthogonal basis for R2, right? So option 7 cannot be true. So all these options are clear for everyone?
Yes, ma'am.
yes, ma'am.
Yes, ma'am.
Okay. So the next topic is projections. Again, projections is a very important topic. So what is the projection of one vector? Let us say the projection of B on A. So projection of B on A. It is given as inner product A comma B by inner product A comma A into A. I'm not going to the details of how we got this. But projection of B on A is this expression inner product A comma B by inner product A comma A into A. Okay. So projection of B on A, first of all, you should know that it is also lying along the same vector A. So it is simply a scalar multiple. This is just a scalar. It is a scalar multiple of A because it lies along the same vector A. Okay. Fine. So this is projection of B on A. So projection of one vector on another vector. Now, instead of just one vector, suppose we want to see what is the projection of V on a subspace. Okay, projection of V on a subspace. Then for that, you need to find an orthonormal basis for W. First of all, find an orthonormal basis for W. Then the projection of this vector V on W is given by this formula. Summation I is equal to 1 to n inner product V comma Vi into Vi. Okay, so here we don't have anything in the denominator because what is inner product Vi comma Vi? Is 1 because it is orthonormal, right? It is orthonormal. So Vi comma Vi, inner product Vi comma Vi, norm Vi is equal to 1. What is norm Vi? Square root of inner product Vi comma Vi. So it is 1. Okay, fine.
Yes, ma'am.
Okay.
Ma'am, could you comment that again?
See, here we had something in the denominator, but there are no elements in the denominator for projection of V on W. Because what is inner product Vi comma Vi? It is 1, right? For an orthonormal basis, Inner product vi comma vi is 1, right? The norm is 1 for each vector.
Yes. Yeah.
Okay, fine. Okay, so considering projection as a linear transformation, everyone please pay attention here. This is again an important topic. So let's say T from V to V is a transformation defined by T of V is equal to projection of V on W. Okay. So now what does that mean? So let us take this example itself. Suppose you are having the vector A. What is the projection of A onto A? You will get the same vector. Nothing is projected, right? Now the same thing. Suppose you are taking a vector from W itself. Okay. And projecting on W. So for example, let us take a specific example of W. Maybe I am taking set of maybe XY axis, W as the XY axis. XY plane, sorry, not XY axis, XY plane. Suppose W is the XY plane. Okay. So now what are all the elements of this W? You know that they are of the form X comma Y comma 0.
0.
Right? So what happens when you project an element X comma Y comma 0? What is the projection of X comma Y comma 0 on W? You are already in W. What does it mean by projecting again on W?
No.
Nothing.
Nothing will happen. You are going to get back the same vector, right?
Yeah.
It means what? So if you are projecting some vector on the same space, okay, so if you are taking a vector from W and projecting, then you are going to get back the same vector. So now what is the range of T then? All the vectors projected are going to lie on
W.
W. And what is the rank of this projection? What is the range is W. Rank is nothing but the dimension
Dimension of W.
W.
And what is the kernel of T?
It's
What is the
nullity.
kernel of T?
Dimension minus rank.
Here that is orthogonal complement of W. Kernel of T is nothing but the orthogonal complement of W. What is orthogonal complement of W? The set of all V in V such that V comma W is 0 for all V in W. So that is called an orthogonal complement. So for this case, XY plane, what is the W perp for this case? Can you tell? In this case, it is very easy.
Is it 0, 0?
Let's take XY 0. What is a vector? Maybe let's say A, B, C. You have to get it to be 0. What is that?
AX plus BY is 0.
Yes, AX plus BY equals to 0.
So AX plus BY is equal to 0 means what is that you are getting?
The kernel.
A and B should be.
0.
Okay. So in fact, you have to do maybe in this way to get the exact space. If you get this, maybe you don't see what is the space exactly. Maybe you have to do with a basis element, then it will be more clear. So let's take a basis element for W, another basis element for W. Now tell me what happens.
A is 0, B is 0.
A is 0, yeah, B is 0.
Okay. So whenever you have to find the perp, just take a basis element of W and take a common element and do the dot product and equate it to 0. Then you will see that A is equal to 0, B equal to 0 means what is that you are getting? Z axis, right?
Yes, ma'am.
So W perp is nothing but the Z axis.
Yes.
Okay, fine. So these are some again properties of the projection transformation. P square is equal to P. Okay, when you do the square, it is going to be the same only. Okay, and norm of P is less than or equal to norm V. Okay, always you see that when you are projecting a vector, the actual size gets reduced. Okay, so you can easily see that the vector B length is bigger than the projected vector. So this is the projected part. This part is smaller than this part, right? The length. Yeah.
Yes.
So you can always remember that from PW of V is less equal to norm of PW of V is less equal to norm V. Okay. Fine. So now you are given a plane spanned by these two vectors. Now, how do you find V perp?
Dot product
Zero,
0.
zero.
So, as I told you, you are given a basis now. You have to now multiply it with a common vector, do the dot product with a common vector, and find the values of ABC. So, if you do this, what is that you are getting?
A plus B is equal to 0.
And
B plus C is equal to 0.
so, from this, what do you get?
B
is equal to minus A.
B is equal to minus A, C is equal
B
to
is
Minus B.
minus C.
minus B, so C is equal to A,
A.
right? So
Yes,
it means
Yes,
your
ma'am.
V perp is nothing but A comma minus A comma A. So this is your V perp, right? Okay. So again here you have two subspaces V W1 and W2. What are W1 perp and what W2 perp? How do you find? So what is the basis element for W1?
1, 0.
X comma 2x.
See, x comma 2x you have. So 1 comma 2.
1, 2.
Yeah. So this is the basis. So when you do the dot product with a comma b, what is that you will get?
A plus 2B.
2b is equal to 0.
So it means 2b is equal to
Minus A.
Minus
so
B.
which option coincides? 2b is equal to minus a.
Third option, third.
So this is incorrect. For W2 you have x comma minus 2x. So what is the
1
basis?
comma minus 2.
1 comma minus 2. So when you do the dot product with a comma b, you get
A
A
minus
is equal to 2b.
A equal to 2B.
yeah. So 2b is equal to a.
Option.
Fourth option.
So do you understand how we are finding the orthogonal complement? Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes. Okay. Okay. So here you are having a choose the correct option. So the first option says that suppose beta is an orthogonal basis of an inner product space. If there exists some vector in V such that this vector is orthogonal to all the basis element, then V is 0. Is that true? How do you
Yes, ma'am.
see? V is any element from V and this is a basis. So can we write V as a linear combination of VI's?
Yes, ma'am.
So now it is given that V comma Vi is equal to 0 for all I. What does that mean? Summation
Zero.
AI Vi
bi.
is 0. This means what?
Vi
Summation
bi
AI Vi
is 0.
right? Now
Vi
what do you
is
know
0.
that Vi, this is norm Vi. Norm Vi cannot be 0. So this is then what does that mean? This means that
Summation AI is 0.
AI is 0.
if AI is 0 for all I, this means that V is 0. All right?
Yes,
AI is
ma'am.
0 for all I,
ma'am.
V is 0.
Yes.
Okay. There exists an orthonormal basis for Rn with the standard inner product. Of course, what is that orthonormal basis? Can you tell? Standard,
Standard order basis.
right? Standard ordered basis is an example of an orthonormal basis for Rn. Okay. So this option is correct. Okay. So again, here is an important property for projection. Range of PW. What is range of PW? We already saw.
W.
W. And what is null space of PW?
0.
0.
No.
W.
No. Okay, what
0
is
vector.
no? It's the W perp, right?
Yeah.
Yes, ma'am.
Yeah.
So W intersection W perp is always 0. Okay. Remember, W intersection W perp is always 0. And another property, I don't know whether you will need it or not. I guess for some problems I have seen that this property was used. This is again based on Rank-nullity theorem, that dimension of W plus dimension of W perp is equal to dimension of
V.
okay, and W intersection W perp is 0. So these are some important properties about W and W perp. Okay. What about option 4?
Ma'am, could you explain like how W intersection W perp is 0?
Okay. Okay. Suppose let us take some element X which belongs to W intersection W perp. Okay. Now this W is there in W as well as W perp means. So you take that you take some basis of W. Okay. Then this X is orthogonal to all vectors of W. And it is also in W. What does that mean? That's what we just saw here, right? Then this becomes 0. Yes or no? See, X belongs to W perp means X is orthogonal to
W.
W, right? All vectors in W. In particular, it is orthogonal to some orthogonal basis of W.
Yes.
So you can say X is 0 from this statement again.
Yes.
Okay.
Yes. Yeah.
Fine. What about option 4? One minus 1, 0, 1 cannot represent a matrix corresponding to some projection. What do you know about projections? P square is equal to P, right? So does this matrix satisfy A square equal to A?
No.
No.
No, right? A square is not equal to A, so this cannot represent a projection. All right?
Yes, ma'am.
Yeah.
How
Yes,
can
ma'am.
we assume in terms of orthonormal?
Sorry.
Like in this case, how can we assume as orthonormal?
Which one? Which one?
Last option.
Why do you think about orthonormal? I don't understand. See, they are asking, so consider this as a matrix representation of the transformation corresponding to some projection operator. Now, is this possible or not? They are asking. If this is representing a projection transformation, then it should satisfy A square equal to A, but it's not satisfying, so this cannot represent a projection operator. What's your doubt here?
No, ma'am. No, actually, I was assuming something else.
Okay, fine. Okay. Consider a vector. We are almost at the end. Okay. So I guess only 2 more problems are there. So consider V is equal to R3 with inner product as dot product. You are given this subspace W and you are given the projection. Find the dimension of the image space PW. What is the dimension of image space? It is nothing but the dimension of
W.
What is the dimension
W.
of W?
1.
X comma X comma
0.
1.
1.
1.
What is the dimension of the null space? You use this property now.
V perp. Dimension of V perp.
So this is nothing but dimension of V minus W perp, which is nothing but dimension of V minus dimension of W from this property. So it is 3 minus 1, 2. Okay, fine. If V belongs to W such that norm V is equal to 3, then find norm of PW of V. So now V is in W. So if V is in W, what do you know about the projection of V? It is in the same space and it is projected again on W.
Also V.
So it should be V only, right?
Yes.
So what's the norm of PV?
V. 3.
3.
Okay, let A be the matrix representation of PW with respect to some orthonormal basis, beta and gamma. Find the dimension of the null space of A square. So what is A square? We already know A square is same as
A.
A. So what is the dimension of null space of A?
One. Oh, sorry, two.
2, right? Okay. All the options are clear? A, B, C, D?
Yes, ma'am.
Yes, ma'am.
Okay. Oh. So Gram-Schmidt process, again, it is involving some formulas. So Gram-Schmidt orthogonalization, given any set of bases, you have to convert to orthonormal basis. Here are the steps for it. Please go through this formula. I'm not explaining Gram-Schmidt process here. Okay. Fine. Please mute. Yeah. An important theorem, any finite dimensional linear product space definitely has an orthonormal basis. Okay. What are orthogonal transformations? A linear transformation from V to V is called an orthonormal transformation if inner product TV, TV is equal to inner product V, V. So if this condition is satisfied, that is the inner product is preserved, then we call such a transformation to be an orthogonal transformation. Okay. So orthogonal transformation preserves length and angle. What does that mean? So if if the angle between V and W is some theta, then the same is the angle between TV and TW. What is the distance between V and W? Is the same between TV and TW. That is the meaning of preserving length and angle. Clear? Yeah. Yes, okay. And orthogonal matrices. So if A is a matrix and it is said to be orthogonal if it is a matrix with respect to a orthogonal transformation and it satisfies this condition, A transpose equal to A transpose A is equal to I. Okay. So such matrices are called orthogonal matrices. Okay. And the rows of A, if the rows of a matrix are orthonormal, then you get this condition. And if the columns are orthonormal, then you get this condition. Okay. So for orthogonal matrix, you have both the conditions satisfied because for an orthogonal matrix, what will you have? Both the rows and the columns will form an orthonormal set. Okay. This is again an important property for orthogonal matrix. Okay. Okay. Let A be a 3 by 3 orthogonal matrix. First of all, if it is orthogonal, you know that the rows and columns are orthonormal, right? So if the rows and columns are orthonormal, what can you say about linear independence of the rows and columns?
They are linearly independent.
Independent.
Columns are linearly independent, right? So if they are linearly independent, the rows of A form a basis for R3. True or not?
True. Yes, ma'am.
The columns of A form an orthogonal set of vectors with respect to dot product.
True.
True or not?
True.
That is what we saw here. True. The rank of A is 2.
False.
No, it's
What
a full
will be the
rank.
rank of A?
3.
3. The system of linear equation X equal to B, B non-zero has infinitely many solutions.
No.
It should have
solution.
Unique solution.
unique solution. So this is also incorrect. So kind of rushed through the last part, but I hope it was clear for you. So if you want more problems, definitely more problems are going to be solved in the TA sessions again for week 5 to 8. Try to not miss any revision session by TAs as well. Okay.
Ma'am, I have a question. If
Yes.
two matrices are orthogonal, then means A transpose, the property which is mentioned there is A transpose into A equals to A into A transpose equals to I. Then the transpose and the inverse of the both matrices should be same.
Yes. So here in this case, in fact, we have A inverse is same as A transpose. Yes. So if A is orthogonal, then this property is there. Okay. Fine.
Thank you, ma'am.
Okay, then.
Ma'am, can I ask a question?
Yes, please.
General question, ma'am. I just want to know, ma'am, for a W, ma'am. Yeah, for the W, ma'am, in the general sense, what is ma'am, W complement, ma'am? In physical sense, what how we interpret, ma'am? For example, W is a subspace, ma'am,
Oh,
that can be
okay,
in
okay. I
plane
understand your question.
R2 or R3, ma'am.
Okay, I understand your question. See,
How we
you want to visualize it, right? Kind of understand it through
yeah,
visualization. Okay, so just the same concept
yeah,
like perpendicularity of vectors.
just ma'am,
Yes, yes.
just
So
little.
what does mean by perpendicular vectors or orthogonal vectors in terms of dot product? What happens?
Theta should be 90 degree.
So you see that if a vector is suppose like this, so maybe 1 comma 0, you know that this is orthogonal to 0 comma 1. Or if you are taking the vector 1 comma 1, then it is orthogonal to 1 comma minus 1. Correct?
Yes.
Yes, ma'am.
Now the same thing, instead of considering a
Yeah,
vector, now I am going to consider x-axis. This is your W. Now what is the line which is perpendicular to this x-axis, which is also a subspace?
Y-axis.
Y-axis, that is your W perp.
Y.
Y.
Yes, ma'am.
Z axis you
Okay.
can also.
And the same thing you can see here. Yeah, suppose you are considering all x is equal to y, the line x is equal to y. Okay, this is your W, let us say. Then what is W perp?
X
W
is
perp
equal
is
to
the
minus
line
1.
perpendicular to it. So you have x plus y is equal to 0.
X is
So,
equal
okay.
to minus y.
So in terms of R3, if you want to see, then what happens? Suppose you are having a plane, for example, the XY R3, I am not good at drawing, so I don't know. Let me try. So suppose you are having the XY plane. We already even saw that if you are considering the XY plane, this is your W, XY plane. We saw that what was your W perp? Is the Z axis.
got it, ma'am.
Okay, you
Got
can
it.
see that it is kind of some perpendicular subspace to the subspace W. That's all. Got it?
Fine, ma'am. And got it, ma'am. Totally got it, ma'am. And just last, ma'am, for the layman understanding, but inner product is equal to, ma'am, dot product, ma'am. But you told inner product this is that specify this particular 4 5 properties, ma'am. For layman, ma'am, for general notion, ma'am, can we say that the inner product is equal to dot
See, inner product,
product, ma'am?
no, inner product is a generalized version of dot product. Dot product is one specific example of inner product. So as we saw in vector spaces, see, in R2, Rn, we first saw R2, R3 and all before introducing what is a vector space, right? So whatever properties are there for vectors in R2, okay, properties of R2, we generalized and called them as vector space. Same thing we are doing here. Whatever properties we observe for dot product, you generalize them. Whatever properties you see for dot product, you generalize it and call it inner product. That's all. Okay? Okay?
Okay, ma'am.
Fine.
Okay.
Any other questions?
Ma'am, how W per is a null space?
Week 9 to 11 when there will be a revision session.
Okay, first maybe I'll answer for the null space part. So someone asked why W perp is the null space of, yeah. So why W perp is the null space of the projection map? Okay. So what is mean by projection map? Here projection means, so here maybe we have to go to the definition. Anyway, so projection, what happens? Everything gets projected onto W itself. Now what happens to the range is W. Okay. Now what is the kernel of T? Kernel of T means your projection, all the vectors should be going to 0. So projection of V goes to 0. So now maybe I won't be able to explain it now using this, but I'll explain it using this. Okay, this is a projection of B on A. Now, suppose this projection of B on A is 0. What does that mean? What does that mean? Projection of B on A is 0. What does that mean? Inner product A comma B by inner product A comma A into A is 0. What does that mean?
Okay, perpendicular.
Your A is a non-zero vector. So it means inner product A comma B is 0. It means your vector B is perpendicular to A.
Okay.
Correct?
Yeah.
So the same you can visualize for a general vector space, general subspace W also. So whatever vectors which are perpendicular, okay, imagine. So imagine even this example I was telling. Okay, imagine, suppose you are projecting this, any vector on this line on W, then what will happen? It will get projected to this point, correct?
Yes.
Same way, if you are projecting any vector on this line, okay, sorry, on this line to this, then it will be again coming to origin only, correct?
Yes, ma'am.
The same you see for R3 also. You project any vector from here, then it is projected to 0. Okay, so that is why we see that the null space of the projection vector is nothing but the W perp. You can visualize it, right? I did not give a clear-cut proof of why W perp is the kernel, but you can see it, right?
Yes, ma'am. Got it.
Okay. Okay. Okay, then I guess it's time to wind up. Thank you very much, everyone. This is the last session for this term by me. There will be one more session by Sanidhi. Thank you, everyone, and wish you all the best.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.